Alright guys, obviously if you're watching the video that means I am out and I'll be out for a little while, but we're going to keep rolling on anyways, but any homeworks that you have, just keep them. It's not the sub's job to check them, but keep up with them because that day I come back I'm just going to take a look at all of them, so don't be putting them off and then you're just going to have too much to make up by the time I come back and you might not know what day I'm coming back, so try and keep up with this stuff. You'll still have assessments even though I'm gone. If you needed extra help, there's two other teachers who teach this same pre-calc honors. It's Mrs. Hall and Mr. Remy. So obviously you can see them after school if you do have questions. But the good thing about the videos is you can pause and rewind to make sure that you understand it. So what you guys want to do when you first get in, there's no classwork today, so you don't need to look in the pile and see if there's anything for you there. Not today anyways. Today we're starting with 1.3, but the day 2 of it. So last class you did the activity. I'll grade that when I get back. But today, what you're going to do is 1.3 reflections, even and odd video. Not quite. We're going to do that a little later. The activity was last class. This is your homework. And so you don't actually need anything just yet. We'll get to this one in a second. This is what you guys are going to do for your homework. It's actually very short. And whenever you finish this video and going through your notes, just open this one up. But if you want to have graph paper open in the meantime, or you want to go get graph paper, you can pause the video and grab it because you can do your notes just on regular line paper or graph paper. So what we are doing is symmetry in odd and even functions. So we really did symmetry a lot last class. Hopefully this is more of a refresher than even and odd is something new. So, just really quickly, if x is replaced with negative x, right? So if you have an equation, if you do an f of negative x, all that's saying for you to do is plug in a negative x everywhere that the x is. Now, 99.9% of the time that's going to change what the equation is, but sometimes it won't. And if it doesn't, then the graph has, or the equation has, what we call y-axis symmetry. It also means that it's even. Those would mean the exact same thing. So y-axis symmetry means it's an even function. So an example of that, if I gave you something like f of x equals, whoops, x squared, right? If I said f of x equals x squared, right, and you plugged in negative x, well, negative x squared is the exact same thing as x squared, right? Because if you square a negative, it's positive. If you square a positive, it's positive. You're going to get the same thing. So these two are the same thing. So f of x equals x squared is an even function. It's an even equation. And it also has y-axis symmetry. So when you think about the graph of it, right, if that's graph paper, it has y-axis symmetry, which just means if you folded it like a hot dog and folded it, the long way, you would get this part of the graph that would merge right with this one and then vice versa. So it has y-axis symmetry. I think that kind of speaks for itself. But we're going to say that that's called an even function today. If you have y replaced with negative y, right, so or negative f of x, if that does not change the equation, then you have something that has x-axis symmetry. This doesn't mean it's odd. It just doesn't mean it's even. It's nothing. It's what we say neither odd or even. But it's just what we call x-axis symmetry. So there's not really, it's kind of counterintuitive. It wouldn't be a function if it had it because it wouldn't pass the vertical line test. But, I guess if you had something that looked like this shape right here, like a sideways parabola right there, right? If you were folded it like a hamburger, right, you would get this part spitting onto this part and then vice versa. So this graph has x-axis symmetry, and if you had to write an equation for this, just means if you plug in negative y instead of y, or negative f of x, same thing, it wouldn't change the equation. So like if you had x equals y squared, plugging in a negative y instead of a positive y would be the exact same thing. It would, for the same reason that this one was. So this equation has x-axis symmetry if you had to graph it. Again, it wouldn't be a function, but it's still an equation, and you would say that it has x-axis symmetry. Now if we do both of them at the same time, if x is replaced with negative x, and then you replace y with negative y, if that doesn't change the equation, right, when you simplify it, then that's what you call origin symmetry, in which case we also call it odd. And this one's pretty easy to remember. Odd, origin, origin, odd. They both begin with O, right? Y-axis is even, not really any tricks you can do to memorize that one. But this one's pretty easy. Odd, origin. So if something has origin symmetry, it's odd. And what does that mean? Well, it means if you like flip the graph upside down, you rotate 180 degrees, it's the exact same thing. So like that's a cubic function. I'll try and draw right now, right? That's a cubic function. And I decided that, it starts in the lower left, ends in the upper right. And not all cubic functions are like this, but this one's y. Say this one's y equals x to the third. This one does have it. So if I was to rotate this 180 degrees, just turn it upside down, it's actually the exact same function, right? It starts in the lower left, ends in the upper right, and then it did that way to start. So that's what it looks like. All you need to know though is if you replace x with negative x, y with negative y, it has that. The last one, if you replace x with y and y with x, so that's what we did last class. It's probably what you didn't get to, but you did in the homework. It's called f of y, right? You're switching the x coordinates with the y coordinates, and in the equation you're switching x with y. If that doesn't change the equation, then that has what we call y equals x symmetry, right? Which just means that identity function, that diagonal line, it would reflect itself over that. So like if an equation would be like x, if I give you like x plus y equals, equals 1. Well, if you switched x and y, you would have y instead of x. And then instead of y, you'd have plus x, right? So all we did was we switched x and y around, but you get an equation that's the same thing, right? X plus y is the same thing as y plus x. So this equation is what we say would have y equals x line symmetry. It just means it's reflected over like it would be, like if we had a straight line that's y equals x, right? It would be like reflected over this. So like this part could be something like over there or something. But those are all the types of symmetries you have. So you want to test each one by plugging in negative x, or in this case negative y, or in this case both negative x and negative y. And the last one, you plug them in, you switch the x's and y's, right? So again, to remember, y-axis symmetry, even function, origin symmetry, odd functions. Again, 99% of the graphs that you see don't have any of them. But obviously from here on out, you'll get some that have something probably. But most of them don't. So like here's this first example, right? If you wanted to test f of x equals 2x plus 1 and see if it had any symmetry, right? The first thing you would do is okay, well, f of negative x, and see what that gets you. So you would say, okay, instead of saying f of x, I'm just going to say y. It's a little easier. So y equals 2, but instead of x, I'm plugging in negative x, and then plus 1, right? So you'd say, okay, well, when you kind of get rid of that negative, you would have 2 times negative x is negative 2x, and then plus 1. And then there's nothing else you can do. You just kind of look at it at this point and say, okay, is this the same as this? No, because this one's negative, this one's not. So does it have y-axis symmetry? No, because it's not exactly the same, right? And then you would do the same thing for negative f of x, which just means negative y. So instead of saying y, I'm going to plug in negative y. So I'm going to say negative y equals the 2x plus 1. And when you get y by itself, right, you're going to get y equals, right, so you'd want to multiply both sides by negative 1 and multiply this whole thing by negative 1. So you get negative 2x and then minus 1, right? So then you would look at this one and say, okay, is this the same as this? Well, clearly no, right? So that one doesn't work. So I'm just putting an x here to show that it doesn't work, not like x like a variable. then we go ahead and say, okay, well, the third one's if we replaced negative y and negative x. So I just do that one as negative f of negative x, just showing that we're doing negative y and negative x. So it's negative y equals 2 times negative x plus 1. Right? So plug in negative here and negative here. And when you simplify that one out, do it in one step, you're going to get, this would be negative 2x, but then you're going to have to use this negative, so it actually goes back to positive 2x. But then this plus 1, when you multiply both sides by negative 1, becomes minus 1. So here, it's close, but it's not the same. So does it have origin symmetry? No. Right? Meaning it's not even, it's not odd, it's neither at this point. And then the last one was f of y, which just means you're replacing x and y. So you're going to get x equals 2y plus 1, right? And so you're going to get x minus 1 equals 2y, and you'll finally get x minus 1 over 2 equals y, right? Clearly not the same thing as the original, which was the 2x plus 1. So none of them worked. Again, this is the case with most equations. They won't work. Obviously, I'll give you some that do work, or else it's a pointless section. But that's how you test each of them. So this line, right, this is still a reflection over the y-axis. This is still a reflection over the x-axis. And this one's still a reflection of y equals x, but they're not symmetrical over those points. And that's kind of the key here. They're not symmetrical over those points. They're still reflections, but they're not symmetrical. And that's all it's saying. So like this one, x to the third, right? You got 1, 2, 3, 4, 5, 6, 7, 8, 8. So negative 2, negative 8 is a coordinate for x to the third. Negative 1, negative 1, 0, 0, 1, 1, and 2, comma, 8, right? Those are 5 coordinates for x to the third, right? If you plugged in negative 2, you get negative 8, and so on and so forth. You do want to get in the habit of plugging in x's. We didn't do a good job of that on the quiz, but, plug in x's, get y's, get coordinates that way. So that's the graph, right? So origin symmetry, I kind of already showed it to you. What does it mean? Well, actually, I can group these together. It just means, again, it starts in the lower left, ends in the upper right, and if you rotated it 180 degrees, it'd be the exact same thing, right? So it's actually negative 2, negative 8. It's the same exact coordinates, left to right, right? It's the exact same thing. So that's what it looks like. So we'll take a look at 4x squared, right? And you can do the testing like we just did with the line, but you could certainly just plug in points. If I plug in 0, I get 4 times 0, which is 0. If I plug in 1, I get 1 squared, which is 1. So times 4 would be 4, and negative 1 would be the same thing. You basically get a parabola that goes up a lot quicker. So you can tell by looking at it, right? Does this have symmetry? Yeah, it has y-axis symmetry, which means it's an even function. And just to kind of prove it algebraically, if you plugged in negative x, right, you would get y equals 4 times negative x squared, right? This is doing f of negative x. Should have started with that. That's what tells you if it's even. So when we do f of negative x, we just plugged in negative x right here. Right? It's the same exact thing. Negative x squared is the same thing as x squared. So you get an equation that's exactly the same, right? Now, if you plugged in negative y, you'd have to make this negative, right? It's definitely not the same. If you switched x and y, it's definitely not the same. You'd have something like y squared, which is totally way off. And then if you plugged in both negative x and negative y, it would actually change too. So the only one it has is even, right? But you can kind of see it has y-axis symmetry. If you folded it like a hot dog, you get the same thing right on top of itself. So now we'll try this one with all 4 tests, and you can pause the video and you can try it. And then as soon as you're done trying it, you can resume the video and just kind of check the answer. All right, so hopefully you've done all 4 tests. So if we do f of, here, I'll do it like this. f of negative x, that's going to equal, right? I'm just going to, not even going to make an equal sign, I'll just draw like an arrow. So we're doing f of negative x first. So when we do it that way, we would get 4 equals, and then negative x squared. Probably quicker if I do it that way. And then plus, and then again, you want to plug in a negative x there, y. And we just want to see if it's the same thing. So you can probably tell it's not going to be. Negative x squared is going to be the same thing, which is good. So it's not like you have to get y by itself here. Right? You get 4 equals x squared. So far, so good, right? We match. 4 equals x squared, 4 equals x squared. And then plus negative xy. You have plus xy here. So the negative is just going to make this minus xy. And that's all that you need to say that it's not symmetrical over the y-axis. So it's not an even function. Right? So that one doesn't work. Then we can go negative f of x. And with this one, we're going to do the same thing, but we're going to plug in negative y. So here we have 4. You know, I'll type it just to be consistent. 4 equals, and then same thing, x squared. I think I can do it like this. Yeah, x squared, and then plus x, but now I'm plugging in, stupid, plus x, but then I'm plugging in negative y, right? I'm doing negative f of x, which is the same thing as negative y. And you're going to see it's the exact same thing. You're going to get this answer all over again. Thought I copied that. There we go. Right, you're going to get the exact same answer. You're going to have 4 equals 4, right? X squared, but then plus x negative y will still make this a minus sign. Although the x is positive, the y is negative, so you get the same thing. The next one is going to be negative f of negative x. So we're switching both x and y. So here we're going to have 4, just probably quicker, equals negative x squared, and then plus, and then we're going to go negative x and negative y. So we plugged in a negative x and a negative y. And what happens with this one is if we actually get it, right, the 4 stays 4. Negative x squared is the same thing as x squared. And then plus negative x times negative y is actually positive xy. So we get something that looks exactly the same as the original, in which case it does have this one. And when you plug in negative x and negative y, if you remember from that first slide, that means it has origin symmetry. And it also means that it's an odd, I shouldn't even say function, but it's odd, right? It's an odd equation. So it's origin symmetry odd. The two go hand in hand. It can't have one without the other. So that one worked. And then the last one is one that you don't have to do as much work for because you can usually see it quicker, right? If you did f of y, meaning instead of x, you have y in there, so you're switching x and y, you would have 4 equals y squared plus yx, right? So I switched out y's with x's. This part's the same. xy is the same thing as yx, but y squared is not the same thing as x squared. You don't have to get y by itself here and prove it. You can probably just see it's not going to work. So it does not have y equals x line symmetry. All right, so again, you can pause the video, try this one on your own, and then I'll go through them after you're done. So go ahead and do that now. All right, so hopefully you've done that. Now here, when you do, well, I'll do f of negative x first. But what's going to happen, I'll just give you the answers here. You would plug in negative x inside here, and then inside absolute value bars, negative x is the exact same thing as positive x. So that one's actually the same, and it works, right? So when you plugged in a negative x, it actually works. I won't go through the whole thing, but you would want to, on a test, show all the steps, show you plugging it in, as simple as the math might be. Please show all that work. Um, but you would have negative x, it was the same thing as positive x here because it's inside the bracket, just like if it was x squared. So this one works. So that means it's even. Well, it has y-axis symmetry, and it's even, right? Those two go hand in hand. It can't be one without the other. Now, when you did negative y, or negative f of x, same thing, you would also get something that works, right? For the same reason, if you plugged in a negative right here, the absolute value of negative y is whatever the positive value of y is, just like if you had positive y to start with. So that one's exactly the same. It doesn't change yet. So it also has x-axis symmetry, which is a little weird. Just means it's not a function, but that's okay. It doesn't mean it's odd or even or anything like that. It's kind of its own separate thing. Okay, so that one worked. Now if you did negative f of negative x, so we plugged in a negative y and a negative x, it would still work, right? Because the negatives would both cancel each other. Well, they wouldn't cancel each other out, but they would cancel out because of the absolute value bars. So those would be exactly the same equation. You would end up with the absolute value of x plus the absolute value of y equals 4. So that one works. And if remember, this one was odd. We're testing for origin symmetry. So it has that as well. And you might be saying to yourself, well, how can something be even and odd? Well, it's not like a number. It's a function, or it's an equation. So it can be. We would actually say this is literally both even and odd. Sounds a little strange, but that's okay. And then the last one would be the f of y, right? So when you did the f of y, you're just switching x and y. So it would literally be the absolute value of y plus the absolute value of x equals 4. And that's the exact same thing as the original equation, right? Those are equivalent. You can do 5 plus 3 and 3 plus 5, and it's the same thing. So it actually has this one too. So the last one, if you remember from the first slide, that means it has y equals x line symmetry, right? And those are the only 4 types that you're ever going to have to deal with, but you want to show all 4 tests every time. So right, I skipped these 3. This one I didn't skip. That's all you would really need to show. But that's it, right? That's kind of the lesson in a nutshell. There is a video reinforcement, right? So it's on, it says Aspen, it's not on Aspen, it's on Schoology. It's 11 minutes, so you can watch that. That guy's on it. Again, that's right on Schoology. It's this video right here. So finish the class by watching that. Once you're done, the homework, it says classwork homework, but you know, if you have time starting class, it's not a lot even if it's all homework, right? All you're doing is looking at these 6, testing each one for all types of symmetry, so all 4 types for each one. So plug in negative x, plug in negative y, plug in negative x and negative y, and then switch x and y, see what you get. And then you got a few textbook problems too. We got 5 there, 7 there, and then like 3 or 4 there. So, and you can make simple graphs of those ones. And that's what you're doing. So certainly if you have questions, you can email me. But, you know, I think hopefully it's pretty straightforward. Again, if it sounds confusing, just rewatch the video.